The problem that we chose is problem 1, which is the block on a turntable attached to some hanging mass. Basically what we have here, we have a turntable of known radius r spinning at a set speed. It's frictionless and massless, and then there's a block on top of it at basically the outer rim attached to a string that goes through this hole in the center of the turntable and down to a sphere of some mass, little m, and the string is wrapped around the sphere multiple times. So in order for this problem to work, we're told that it's a frictionless turntable, but if it was truly frictionless, then when the turntable spun, the block would stay in place. So instead, in order to work out the problem, we're going to assume that the turntable is completely frictionless laterally, so there's not going to be any friction forces that we're dealing with. However, the block is still going to rotate with the turntable at the same speed once it gets going. This is pretty much just for the sake of being able to solve the problem. It won't actually affect any of the numbers. So our variables that we have, we've got our capital R, that's our radius of the turntable. We've got our little r, which is the radius of the hanging sphere. And from the problem, we know that the hanging sphere is hollow. So we can assume that it's a completely hollow sphere. We've got our big M, which is the mass of the block on the turntable. We've got our little m, which is the mass of our hanging sphere. We've got our I sub m, which is the moment of inertia for the hanging sphere. Because it's hollow, we know that that's going to be 2/3 little m, little r squared. And then finally, what we're trying to find is the angular velocity of the block. That's also going to be the angular velocity of the turntable. That's what we're solving for. And then we've got our assumptions. Again, frictionless turntable still rotates around, but frictionless, no force due to friction, block's moving with it. We've got that this is taking place on Earth or an Earth-like system, so our gravity is going to be approximately 9.8 meters per second squared. We've got a uniform mass density for the block and the sphere. We've got a perfect massless pulley, doesn't impart any friction, doesn't have any mass, so it won't really show up aside from redirecting the tension force. We've got an ideal string, inextensible, massless, and then again, massless turntable, frictionless, infinitely thin. For our system here, we've got our side view of it, we've got our top-down view with the block around the side, and then the string going out over our perfect pulley, down, wrapping around the block, wrapping around the sphere. We've got our free body diagrams here for our sphere. You can see the tension force is going up, it's wrapped around, and then the force of gravity is going down from the center of mass. We've got our block, it's got a normal force up from the surface of the turntable. It's got a force of gravity down on the center of mass, and it's got a tension force out to the right from the string. Now, the tension force on the block and the hanging sphere are going to be the same, and those are all also going to be equal to the force of gravity on our sphere. Finally, we have our coordinate system. We've set it up where positive x is to the right, positive y is downward. This means that our force of gravity will be positive, our tension force on the block will be positive, and it also means that if we're looking at the forces on the block, we have a positive tension, then it hits the pulley, it rotates, it remains a positive tension, and also because this tension force is negative and this tension force is positive, because of the axes we've chosen, they're going to be opposing. It's just a little easier to deal with. You would get the same result if you did it otherwise.
Now that we've drawn our diagrams and set up the problem, now we can move on to calculating. So first we want to represent our principle symbolically. Using Newton's second law, we can look at the net force acting on each of our masses, both the hollow sphere as well as the block. Newton's second law states that the net force acting on each of those objects is going to be equal to their mass times acceleration. Further, we can use Newton's second law of rotational motion, which is that the net torque acting on specifically the hollow sphere, because we know that it's going to be rotating, is equal to its moment of inertia times its angular acceleration. And we also can represent this by its radius cross the force acting on it that's causing the rotation. And because in this problem, we know that the distance from the center point that it's rotating around is perpendicular to where the force is acting, we can write this as RF sine theta, where theta is 90 degrees, also 1, making this just RF. Now coming back over here, we want to know what our angular acceleration of that hollow sphere is, and we know we can represent that as the tangential acceleration over the radius, as well as we want to know the centripetal acceleration of the block traveling around the disk, and we can represent that with angular velocity squared times some radius. This would technically be big R in this scenario, but this is just to represent it initially symbolically. Now moving over to actually solving the problem off, we redrew our free body diagrams over here just so that we can reference them while solving. We first wanted to look at the net force acting on block big M, and we know it's just equal to the tension force as the normal force and the force of gravity both cancel out. And we know that this is mass times the centripetal acceleration required to hold it in its path around the disk. Further, if we look at our hollow sphere, we know that the net force acting on it is little m times the acceleration of the little mass, and we can see that this is equal to the force of gravity minus the tension force right here. Now, since this is a rotating body, we know that there's some torque acting on it, and we can represent the net torque as equal to the moment of inertia of the sphere times the angular acceleration. And we know that the moment of inertia of a hollow sphere is 2/3 its mass times the radius squared. So using this relationship, we can plug it in, and using our previously stated relationship of the angular acceleration, we can write our net torque as equal to 2/3 its mass radius squared times the acceleration over r. And then we also know that net torque can be represented as the force times the radius because of the perpendicular distance from the point of rotation. And if we set these two equal to each other, we can solve for the force of tension. And solving this out allows us to reach 2/3 acceleration times its mass. Now we can use that relationship and plug it back into our initial net force equation for this sphere. Plugging in for the tension force, we know that the force of gravity is equal to the mass of the hollow sphere times gravity. And we can say that the mass of the sphere times its acceleration is equal to its mass times gravity minus the force of tension. Plugging in what we found the force of tension, we were able to calculate its acceleration to be 3/5 g. Now we can come over here and use our previous relationship of the force of tension is equal to 2/3 AM, and plugging in AM, we get the force of tension is equal to 2/5 gravity times the mass of the hollow sphere. And then lastly, we can use our initial representation of the net force of the big M block, and knowing that its centripetal acceleration is equal to the angular velocity squared times big R, the radius of the disk, we can calculate for the angular velocity of the block as square root of 2 gravity mass of the sphere over 5 big R big M. Now we can plug in some numbers. We were not given any for this situation, so we picked some. Gravity is 9.8 because we assume we are on Earth. Little m, we decided would be 2 kilograms, big M 3 kilograms, and R is 1 meter. Plugging in gives us an angular acceleration of 1.6 radians per second.
Okay, so we have our assumptions and we've calculated the answer. Now what do we do with the final answer, and how do we know that it makes sense? So first we can do a quick unit check to make sure that we didn't do anything weird with our calculations. So first we have gravity times mass divided by mass times radius. And when you bring out the units for that, you then get kilograms over kilograms, mass over mass, and then that just leaves you with seconds squared, leaving us with the correct answer, which is angular velocity is equal to rad per second. For our next part of making sure that the answer makes sense is the actually testing real values. So in the calculate section, we already did a check, but this one will be with a real vinyl record, so we can compare how these masses impact the answer. So this is what a typical record would have per second, and then this is what we have when we input these two values. As you can see, for mass here, the small m, it's in the numerator for our original formula, and we know that that as that goes smaller, then the angular velocity will also decrease. And then over here, we know that that makes sense because as little m goes greater, then there will be more tension pulling it that way. And because of that, that will cause more circular rotation. Because we know this answer makes sense because it makes sense that it is greater than what we would typically expect with a vinyl. So knowing this, we can now also apply that reasoning to these other aspects, the variables of the final equation. So for here, we have big M as it goes to 0, angular velocity will increase to infinity. This makes sense because the smaller the mass is here, the less force it'll take for it to spin, and assuming that force is equivalent and mass decreases, then acceleration will have to increase, and therefore, so does angular velocity. For radius, we have, as it goes to 0, angular velocity increases to infinity, and we know that this is the case because as it's further from the center or closer to the center, the block's angular velocity must increase to fit with this equation. And it also makes sense because we know that if it is farther out, that it'll have fewer, angles per second.
All right, so the first problem that we chose to compare this to was a problem from Studio where we have a pulley with mass, and from it are 2 different spools. Spool A has the string wrapped around it multiple times, and spool B is just secured to the rope so that it won't spin. What we were doing for this problem is we were finding the tension force to see which one would fall first, basically. We chose to compare our problem to this problem because they both involve spools that are spinning. They also both involve tension forces that are equal. In this case, they're in the same direction, they're not in opposing directions. But some of the differences between this problem and our problem was the pulley had mass. In our problem, the pulley didn't have mass. The masses were equal. We chose to solve it with differing masses, but potentially we could have solved it with equal masses. Tension forces were not opposing. And then another similarity would be that we had one rotating mass attached to the string and one mass that wasn't rotating. Just so happened to be that in our problem for this time, the non-rotating mass was at a 90-degree angle as opposed to being parallel with it.
The second problem that we decided to use to compare to our problem that we made this video on is the homework activity 2 from homework 4. In the problem, we had a rotating disc similar to our problem, could be seen as a turntable. However, this turntable had mass, unlike the problem that we were given for this activity. This turntable was given with a radius, an initial angular velocity, as well as we were told that there was a 20-kilogram brick placed directly on the edge of this rotating disc. Now this problem, we decided to compare it because of the similar setup with a rotating disc with a mass placed on the edge. However, we were able to solve this problem extremely differently from the problem we solved earlier in the video, as we were able to use the law of conservation of momentum because the angular momentum in this problem is conserved, while in our problem we clearly see that not only do we have angular momentum in the spinning block as well as the rotating sphere, we also have translational momentum as the sphere gets lowered down. In these two quantities don't have the same units, thus we cannot compare them. But in this problem, we were able to use angular momentum. Further, when we were solving for the angular momentum before and after the brick collided with the disc, we had to treat the brick as a point particle, and this was because the radius between the brick in the center of the disc was large enough where the moment of inertia of the block or of the brick could be directly compared to a particle. Further, this problem was also similar in that the disc had no friction as there was no force slowing it down as it spun. except from the collision with the brick. And then this problem was also similar to the problem we looked at earlier, where the disc was spinning at the same angular velocity at the end as the disc.